So a common situation that comes up if you're doing any kind of research is one where you've gone out and you've collected your data and you want to come up with some kind of function, some kind of formula that describes the relationship you think you're seeing. Maybe it's an exponential function, maybe it's a linear function, maybe a logarithmic function. We're going to be talking about those shortly here. Something with polynomials or square roots, it's some kind of formula. Now, what we're going to be interested in is distinguishing between data that's exponential versus data that's linear. Now, one way to do that is to take a look at a graph of your data. If your data is forming a straight line, pretty good guess it's going to be linear. If your data is increasing really, really quickly, maybe an exponential function is going to be a better choice. And that's a fine place to start. But remember, working from a graph, we talked about this earlier in the class, it's always going to be hit or miss. It's always going to be an approximation of what's really going on. What we like is some more analytic, or some more calculation-based way of distinguishing between these two situations. So before we look at some examples, I want to make two observations here that are going to help us answer this question. Right, so first, suppose we have just a generic linear equation, right? Y equals mx plus b. And what I want to know is, what is f of x plus 1? Right, so if I put x plus 1 in there, formula becomes this. F of x plus 1 is equal to m times x plus 1 plus b. Okay, suppose I subtract these two. Right? Suppose I take the difference of those two successive y values. Well, what happens? Well, I get this expression here, but if you simplify this, and you can do the algebra yourself here, you end up with the whole thing being equal to m. Okay, so what I want you to take away from this is, if we have a linear function, and we take the difference of two successive values, f of 1 and f of 2, f of 47 and f of 48, f of 1,000, f of 1,001. The difference between two consecutive values is always going to be not just a constant, it's going to be the same, or we're going to get the same number every time. Okay, hold on to that. All right, hold on to that, and let's do the same thing for an exponential function. All right, so say we have this generic exponential function. F of x equals a times b to the x. So I'm going to do the same thing. I'm going to say, what's f of x plus 1? Well, that's a times b to the x plus 1. Okay, and this time, instead of subtracting them, I'm going to divide them. Right, so I'm going to do f of x plus 1 divided by f of x. That's a b to the x plus 1 over a b to the x. Simplify the exponents, cancel the a's. That comes out to a constant. It comes out to the base, specifically. Right? So same kind of relationship here. If we take two consecutive values from an exponential function, f of 3 and f of 4, f of 9 and f of 10, same thing as I did with a linear one, the ratio will always be constant. Okay, so let's see how we can apply this. I've got some data here for us to look at, and I'm going to confess right up front, I generated these values in a way that was designed to make them look like what they aren't. Okay, if you look at the first one, it looks like those numbers are increasing really fast, which is what we'd expect from an exponential function. And if you look at the second one, it looks like they're increasing really slowly, which is maybe more likely to be a linear function. Don't trust what you think you're seeing when you've got a rule you can apply to do some calculations and know for sure. Okay, so what I'd like you to do, you can pause if you like, and calculate these other two columns. Delta y in the first data set, for example, in row 2, that would be 25,685.13 minus 13,342.57, and so on down the column. And in the fourth column there, you're going to do the same thing, but you're going to divide. So the value in row 2 would be 25,685.13 divided by 13,342.57. So you can pause if you like and fill those out. Then I'll show you my numbers. So here's what I'm seeing. The difference between two consecutive values is a constant. That is a absolute giveaway that this is a linear relationship. The slope is really big. I mean, that's the slope that we're seeing there, right? The slope is 12,342 and a half, more or less. So yeah, it is increasing really fast, sure, but it's increasing at a constant rate, which is what makes this a linear relationship. And if you look at the ratios, yeah, they're all different. Right, so definitely not exponential. Okay, so we do the same thing over here on the other side. I think you can see right off the bat that the differences aren't going to be constant, right? If the difference 0.010, 0.0102, and so on, definitely not a linear relationship, even though the numbers are small and not changing very fast. Right, but look what happens if we look at the ratio. The ratio is constant at 1.01. That's telling me that while this is a very slow growing exponential function, right, it is nevertheless an exponential function. So in our next lecture, before we move on to solving equations, which is really what I want to get to next, but before we do that, there's a special number. It's called it's symbolized with the letter E. It's kind of in the same category as pi, right? It's one of those irrational, never-ending, never-repeating numbers, and it shows up a lot in applications of exponential functions and logarithmic functions. So we're going to take a little time, talk about that, right? So you're familiar with that value. Then in the lecture after that, we're going to circle back and talk about solving exponential equations.